Hello, my name is Paulo Passos and I will be presenting the paper entitled Computer Studies of the Operation of a Three-Phase, Four-Wire Shunt Active Power Filter Applied to the Industry. A shunt active power filter is an equipment used to compensate in real time harmonics, current unbalance in case of a three-phase installation, and power factor of an installation through the production of reactive power and harmonic currents. The chosen filter topology for this study consists of a 4-wire voltage source inverter which uses 8 IGBTs and a capacitor in the DC link. The use of a 4-wire topology allows us to compensate the neutral current in the system. The image in this slide presents the control diagram block. The algorithm starts by calculating the necessary power to properly control the DC links, and then it is applied the FPD power theory, which allows us to calculate the grid current reference, resorting to a PLL because the grid voltage can be distorted. The calculated reference current is compared with the grid current in order to minimize the error. As the factory under analysis has taken a step forward in the Industry 4.0, it has employed different power quality analyzers through its system. For this study, two groups of loads are considered. One group is the AVAC system, which includes two types of air treatment units and 5 equal chillers. A second group, that will be presented later, is composed by the electrical switchboard of the production lines. The characteristics of the equipment were extracted from the constructor's plate, and the average monthly values are provided by the energy platform of the factory. The values were compiled in terms of current, apparent power, current distortion, and power factor. These values can be checked in the presented tables. In addition to the data presented in the previous slide, it was possible to obtain the waveforms of the loads at specific time frames through an Excel file generated by the analyzers with several points of the current waveform. This allowed to understand the current profile of the loads under analysis as well as to perform the fast Fourier transform in order to obtain the harmonic spectrum. The sequence of the image are from top to bottom and represent phase 1 at the top and neutral at the bottom. In case of the chiller, this equipment has no neutral connection. The same procedure as explained before for the AVAC system was applied to the electrical switchboards of the production lines. Each of these electrical switchboards supports up to 4 production lines. The table at the top presents the average monthly values for the current, apparent power, current distortion, and power factor. The 4 images presented here are the current waveforms of the electrical switchboards, where top left image is phase 1 and bottom right is neutral current. The images should be read from left to right. In order to validate its correct functioning with the factory loads, two different situations were designed. For both situations, the filter only starts its operation after the instant of 0.2 seconds. And the considered loads are 5 chiller equipment, 2 AVAC electrical switchboards, and 10 electrical switchboards that provide power to the production lines. In the first scenario, it was considered that the 5 chillers and 12 electrical switchboards in operation. However, it is considered that the 5 chillers and the 2 AVAC electrical switchboards are on the load side, and the remaining 10 electrical switchboards are on the grid side. This means that the 5 chillers and the 2 AVAC electrical switchboards are being compensated by the filter, while the remaining 10 electrical switchboards are not being compensated. We can observe that the neutral current value was reduced from 642 amps to 65.7 amps. From the presented table, we can also observe that the current distortion of the phases was reduced to almost half. In this case, we can observe the loads being compensated. These loads are the 5 chillers and the 2 AVAC electrical switchboards. We can observe that the loads are being completely compensated as the waveform after the filter's actuation is sinusoidal. It can also be seen that the current distortion was drastically reduced. It drops from values of 45% into 4%. In the second scenario, the inverse is done. That is, the 5 chillers and the 2 AVAC electrical switchboards are now on the grid side, and the remaining 10 electrical switchboards are on the load side. Thus, the 10 switchboards are being compensated by the developer filter, while the 5 chillers and the AVAC switchboards are not being compensated. As we can see, similar results were obtained, where the current distortion dropped to half its value and the neutral current was reduced from 640 amps to 37.2 amps. Here we can see the loads being completely compensated. These loads are the 10 electrical switchboards that supply the production lines. We can observe that the loads are also being completely compensated since the waveforms after the filter's actuation are sinusoidal. It can also be seen that the current distortion was drastically reduced. It drops from values of 47% to 4%. Analyzing the results in the simulation of the two different scenarios, we can verify a reduction of the current distortion, a reduction of the current in the neutral, as well as a balance of currents among the three phases. In the simulation presented in the scenario 1, there is a reduction of about 42% on the current distortion, and a reduction of around 53.3% of the current in the neutral conductor. Regarding the simulation in scenario 2, there is a reduction of about 10% after the filter's operation in terms of current distortion, and a reduction of about 94.2% of the current presented in the neutral conductor. It can also be seen that after the filter's operation, the currents are always quite identical. This means that the filter was able to balance the current in the three phases, which translates into a balanced system. I want to thank to the European Structural Investment Funds for supporting this project, and thank you for your attention.